In this video, I'm going to introduce you to a powerful technique of integration known as U-Substitution. Before you attempt the problems in this video, make sure that you've mastered integrating powers of x through the power rule. We're going to use this on powers, but they're not just going to be powers of x, they're going to be powers of some function of x. So in order to introduce you to U-Substitution, first we have to recall the chain rule, because this is basically the chain rule backwards. Okay, so let's talk about the chain rule a little bit. Let's say that you have a composition of functions here. Now usually I would write this as f of g of x, but U-substitution is usually presented in terms of a new variable called u. So I will represent the chain rule in terms of that new function u. So instead of saying that the composition is f of g of x, I'm going to call the inside function g of x a letter u, so this is the inside function u. Then the composition f of g of x would be f of u. And let's say we wanted to take the derivative. That would require the chain rule because it's a composition. The derivative of f of u would be the derivative of the outside function f prime evaluated at the inside function u and then multiplied by the derivative of the inside function u. That's the old chain rule. You remember that one? Well, in case you're a little rusty, I've got an example laid out right here. A classic example would be when I tell you I've got a polynomial here on the inside, and then I've raised that to a high power, and then I want you to take the derivative. Okay, so here we have x cubed plus 4 on the inside, that's going to be our u, and then we have to the 8th power on the outside. Now when you're taking the derivative of this, you bring down the 8, that's in the exponent right there, and then you leave the inside function alone and you raise that to the 7 because 8 minus 1 is 7. And then don't forget, this is where I say don't forget the chain rule, then you multiply by the derivative of that inside function. So I want you to practice this again using the u terminology. We're going to let the inside function be called u, so u is going to be x cubed plus 4. And so the term that says f prime of u right here is going to be 8 times u to the 7. And then the u prime is the 3x squared right there. Okay, so hopefully you're comfortable with that because now let's use it backwards. Now we've been going backwards for a while. We're doing antiderivatives or integrals. And the goal of this is to be able to write down some function where the answer here, if I take the derivative of it, I'll get the statement inside the integral back. Alright, now the statement inside the integral is x cubed plus 4 to the 8th, then 3x squared. Remember, the thing inside the integral right here is already the derivative of something. The something that it's the derivative of is our goal to find. Keep in mind, when we took the derivative of this function right here, we had a 3x squared pop out. That was due to the chain rule. Now here, this is already the derivative of something. What is it the derivative of? That's what I'm going to find out. But notice that it has the 3x squared, just like the derivative of that had the 3x squared right there. So that gives me a hint. Why don't I let the inside function here be equal to u? Now usually you're going to use this technique on something where it's obvious what kind of inside function you have. If you have a bunch of parentheses and then you have a function inside those parentheses, that's usually a good choice for the inside function. Okay, so we're going to let the inside function be called u, and that's usually going to be the thing inside the parentheses. Alright. Now remember, when I took the derivative here, I had a u prime pop out right here. What I'm going to do right here is I'm going to take the derivative of both sides. I'm going to do it in a little bit of a funny way. Now usually when you take a derivative, when you take the d dx, you get the statement that du divided by dx is equal to whatever the derivative is on that side. That's the usual way we do it. But now we're in integral territory, and when we have the integrals, you see we have this little thing hanging out at the end of every integral. That's called the differential. That's what closes off an integral. If we want to recast this into some sort of integral in terms of u, which is what we're going to do, we're going to end up having, instead of a dx on the end, we want to write this as something, and there's going to be a function of u inside here, and that's going to be closed off with a du differential at the end. Alright, now that's why after I defined my u, I took the derivative right here, and what I'm going to do is I'm going to sort of multiply both sides by dx, so that this statement right here becomes the statement that du is equal to 3x squared dx. Okay? Now why did I want to do that? It's because I'm trying to rewrite the integral in terms of my inside function u. And you can see that if I let u equal x cubed plus 4, which is right there, then really what I have here is I have u to the 8th, right? I have u to the 8th power because I have x squared plus 4 to the 8th power. And remember, if I have an integral, whatever letters I have here, I have to close it off with a corresponding differential, and the letter on that differential must be the same as the letter that I'm using in my function right here. Okay, so I have u to the 8, and look at this, this is really convenient. When I take the derivative of what I've defined as u, I get the fact that the differential du is equal to 3x squared dx. But look, that's what I had right here in my integral. So this part of my integral right here is actually equal to the du. So actually what happens is, when I take my integral as a function of x, and I let u equal that inside function, my integral gets translated into, turn it into an integral du. See, I started with an integral that was in terms of dx, and it had all these x's in it, and now I've turned it into an integral, which is in terms of du, and it has all these u's in it. But the reason I did it is, this one's pretty easy. It's a lot simpler now that it's in terms of u than it ever was when it was in terms of x right there. In fact, it just says the integral is now u to the 8th du. Alright? If I asked you what the integral of x to the 8th dx was, you would say x to the 9th over 9. And likewise, if I ask you what the integral of u to the 8th du is, you're just going to say it's u to the 9 over 9 plus c. You see, I've just changed the letters, but by changing the letters, I've made this integral, which seems really hard, become this integral, which seems a lot more doable. So I'm going to do this integral, and then I'm going to replace the letter u with whatever it was in terms of the letter x. Okay, so I've gotten to this point where after I recast the integral in terms of u, it's u to the 8th du. That turns into u to the 9th over 9 plus c. And what's u? Well, u is equal to x cubed plus 4. So the answer is s cubed plus 4 divided by 9 plus c. And that's going to be the total answer. Let me write that a little neater. Okay, so really what happened right here was that I turned this into the integral u to the 8th du, and that's u to the 9th over 9 plus c, and u is equal to the quantity x cubed plus 4 to the 9th over 9 plus c. And there you go, that's going to be your answer. So, to review, the key of the integration technique of U-substitution is choosing an appropriate inside function to call your u, rewriting your integral so that it looks a lot easier in terms of u, and while you do that, you have to turn your dx into a du using this derivative trick over here. And then after you get the answer in terms of u, you just replace the u's with the x's, and then you get the answer back. Now, I'm not totally satisfied and done until I can prove to you that I am totally positive that this was the answer to the question. Okay? The original statement was that integral that I've got right here. And so now I'm going to take the answer that I got, and I'm going to use the chain rule to get the derivative and make sure that I do indeed have the answer. Okay? So the original integral was this. I'll just copy it down over here. 3x squared dx. And I'm claiming to you that the answer is 3x4 to the 9th over 9 plus c. Well, let me make sure that's true. I'm going to take the d dx of x cubed plus 4 to the 9th over 9 plus c. Of course, the plus c part always just goes to 0, so I don't even really need to write that in there. When I take the derivative of this, the 9 comes down to cancel that 9. And then I have the stuff that was on the inside now to the 8th, because that's 9 minus 1. And then don't forget the chain rule that I'm going to have the derivative of the inside function right there, and canceling the 9's, check that out. I get exactly the statement that was inside the integrands that I was asked to compute. It's perfect. Great. That's called U-Substitution, and we're going to use this quite a bit. So now let me give you another example. Okay, so keep in mind that each one of these examples is going to have something that you want to define as U. Usually that thing is going to be inside a set of parentheses. Alright, now what if I ask you to integrate this function right here, dx? Now this looks like a pretty hard integral. I'm asking you to come up with a function that if I took the derivative of that function, I would get this weird looking rational function right here. Oh geez, at first you might think that's really hard, but then you start thinking, wait a minute, look at that set of parentheses. What's inside that parentheses? X to the 4 plus 5? Okay, let me see what would happen if I defined an inside function, which is a function that's inside those parentheses. Alright? Now, let me take the derivative on both sides, similar to what I did over here, except I'm just going to do the du on this side and I'm going to leave the dx on the other side. Now, again, the reason I do that is because I have the presence of this dx differential right here. And so when I take the derivative on this side, u goes to du. When I take the derivative on this side, I get the derivative of x to the 4. The 5 goes to 0, and then I'm going to put the dx on that side. Once again, this is exactly the same thing as taking the derivative du dx, but I just moved the dx to the other side. I moved the dx to the other side because I've got the dx closing off my x integral right here, and what I want to ask myself is, once I define a new variable u, am I going to be able to have the du inside to close off my new u integral? If I can't find a du, then I'm not going to be able to write the integral in terms of u, because the integral in terms of u has to have an integral and then a du on the other side. Okay, but do you see it there? That's right, it works out perfectly. The du that I get out of here is 4x cubed dx, and look at this, 4x cubed dx, that's my du right there. That's great. So it's going to work out great if I define u as that, because what I'm going to get is this whole blob that I circled on top is equal to du. And on the bottom, I just have u to the 3rd. That integral looks a lot easier. In fact, it'll look even easier once I bring the u to the top and write that as a negative power. And then I've just got a classic power to integrate. Now hopefully you feel comfortable having done all that practice integrating the powers before. And the answer is going to be u to the minus 2, because minus 3 plus 1 is minus 2. Then we have to divide by that same minus 2 so that they would cancel out for each other. And then we just have the plus c. Okay, but remember, the original question was posed as a function of x, so I cannot give the answer as a function of u. I must replace the u with what I defined it to be, and so the answer is, it's the quantity x to the 4 plus 5 to the minus 2, because that's what the u was to begin with, divided by minus 2 plus c. Am I sure that's the answer? Well, I can always check my work. That's the great thing about integrals, is that they're derivatives backwards. So if you're used to the derivatives, then you can surely check the integrals. So in order to check my work here, I'll just take this and I'll take the derivative of it right now. Okay, so let's perform a check right here. I'm going to take the d dx of the quantity x4 plus 5 to the minus 2 over minus 2, and the plus c, of course, always going to 0. So then the minus 2 comes down, it cancels that minus 2, x4 plus 5 becomes to the minus 3, And then, don't forget the chain rule, 4x3. Okay, alright, and what was I asked to integrate? I was originally asked to integrate 4x3 divided by that stuff cubed. Cancel, cancel. And if I rewrite this derivative with the negative exponent appearing as a positive exponent on the bottom, I sure enough get exactly the thing that I was asked to integrate. That's awesome. Now I can integrate not only powers of x, but I can integrate functions of x raised to a power. Okay, it does get a little bit stickier than this. Sometimes this works out perfect, where your du ends up exactly as you need it, right inside the integral. And sometimes it's not so perfect. Sometimes it's like you sort of have the du, but you don't entirely have the du, and that's going to be my next example. So let's try this integral, where I have 6x to the 5, 9x to the 6, plus 7 to the 6 dx. Now once again, I have a feeling I'm going to need the U-Substitution technique because the inside function, it looks like there's an inside function right there. There's like something in parentheses to the 6, right? That's what usually ticks you off that you might want to try U-Substitution. And then when you think about what you use for your U, you should be able to see its derivative also present in the integral. Okay, so what are you thinking? What are you going to use for the U here? The thing inside the parentheses, of course. Yeah, let's always try that first, okay? Now, as soon as you defined your U, you've already inherently also defined your du, because your du is going to be exactly what happens when you take the derivative of your U. Instead of writing du dx on one side and the function on the other side, I move the dx to the other side, and that's because I have a dx right here that I'm trying to replace with a du. Okay, well in the last examples, I actually had this statement right there in my integral, waiting for me to replace it with a du. But I'm not so lucky this time. Check it out. I actually have u to the 6th right here, right? So my integral, this part right here, becomes u to the 6th. But then I have 6x5 dx. Dang it, I wish I had 54x5 dx. Then I would just write du right there, and I would just do it just like the others, right? But I don't have 54, I only have 6, so what am I supposed to do? Well, 54 divided by 9 turns out to be 6, right? So actually, if I take 54 and I divide it by 9, that actually, here what I'm trying to say is that if I take this and I divide it by 9, because 54 divided by 9 is 6, I get 6x to the 5 dx. Now if I want to divide this side by 9, then I should also divide this side by 9. So fair enough, that's equal to du over 9. Why would I do that? Well, I'm just trying to match what I have here because I wish that I could replace what I have right here with a function du, right? So I'm not lucky enough to have exactly what my du should be, but it turns out I have what my du over 9 would be. And du over 9 you can see as the same thing as 1/9 times du. Okay? So because that's what I have right here and that's what I have right there, I'm going to replace this with 1 over 9 times du. That's actually alright. That's not so bad because 1/9 is just a constant. And so by the constant multiple rule, I could just pull the constant right outside the integral. Okay? So once again, if you don't have exactly what you need to match the du here, you can divide both sides of the equation by a constant if it's going to be able to let you replace what you have in the integral with du times a constant. That's what I'm trying to do here. And so what I end up getting here is I get u to the 6th times 1/9 of du. And due to the constant multiple rule, I can pull the 1/9 right outside the integral. And so then I have 1/9 u to the 6th du. I'm just trying to make this as easy as possible. And finally, I've arrived at an integral that's somewhat easy to compute. That u to the 6th is going to end up as u to the 7 over 7. And that 1/9 is just going to carry right through just like there. And then I'm going to have a plus c. Okay? Sometimes it gets like that. Yeah, so that's what you got to do. All right? And I'm not done yet, because if they give me an integral in terms of dx, I have to give them back an answer in terms of dx. And so really what I have over here is I have u to the 7 over 63 plus c. And so in terms of x, u is equal to 9x6 plus 7. So that's 9x6 plus 7 to the 7 over 63 plus c. Well, that's what I claim is my answer. Is that really my answer? I can always check. So I'm going to go ahead and check. Okay, so I'm going to take a d dx at this point, because now I'm trying to check my answer. So the derivative of this is that a 7 comes down and goes on top of the 63. Then I get 9x6 plus 7, and I'm going to get that to the 6. Don't forget the chain rule. Then I have to multiply by 54x to the 5. Is that my answer? Let's see, going to be a bunch of canceling going on right here. Let's see, 7 over this, that's 1 over 9. And then 9 divided by 54, that's going to turn into a 6. So really what I get is 6x5, 9x6 plus 7 to the 6. Oh, check it out. That's exactly what I was trying to integrate. All right, it actually still is able to work out, but in addition to the u trick, we had to divide both sides by an appropriate constant. Would you like to see that one again? Yeah, me too. Okay, so let's do that one again. Not that same one, but a similar one. Because the truth of the matter is, when you're using U-substitution, most of the time, you're going to be off by a constant on your du. You're not going to have exactly your perfect du, but you're going to have it up to a constant. Okay, so let's look at this question right here. X to the 4th minus 8x plus 3 to the minus 5 times x to the 3 minus 2 dx. Okay, the first thing I want to say is that sometimes this question will appear in the following form. Sometimes you're going to have that stuff that I've written as a negative power on the bottom like this. All right? Now, if you see a question like this, I would recommend taking that stuff on the bottom and rewriting it so that it goes up on the top. You're going to end up having to do that anyway so that you can use the power rule. So I'm just letting you know that, but I've already done that step for you and presented the integral with the negative power on top. Once again, we see a polynomial that's inside parentheses and then raised to a power. And our best bet is going to be to let u equal whatever thing is inside that parentheses. As soon as we do that, we're going to take the derivative right here, leaving just the du on this side and leaving the dx on the other side. And that's because we're trying to match what we have here with what we actually have in the integral. All right, what does it look like to you? Does it look like it's going to work out? Well, here, if I define u as the stuff in the parentheses, I need a du that's 4x cubed minus 8 dx. But what do I have? X cubed minus 2 dx? Are these things off by a constant multiple? That's okay. As long as they're just off by a perfect constant multiple, you can still do the problem. But what you need to do is you need to make this side of the equation look exactly like the thing that you have right over there. Okay? So in order to make this stuff look like this stuff, what should I do? Divide it by 4, exactly. You see I got an x cubed here, but I have 4x cubed over here. So I need to divide this side by 4, and don't forget, you have to do that to both sides of the equation. If I divide it by 4, then what I get is x cubed minus 2 dx. And what's that equal to? It's equal not just to du, it's equal to du over 4, because I divided both sides by 4. But I had to do it because I had to match exactly the thing that I had in the integral, right? So now what am I going to do? This integral is going to become the integral of u to the minus 5. And that part right there is going to be replaced not by just du, but replaced with du over 4. But that's okay, because we have the constant multiple rule, and this is just 1/4 times du, so I'm just going to pull the 1/4 all the way outside, just like that, and then I'll have u to the minus 5 du, and that's not so bad. That's going to be u to the minus 4 over minus 4, right? Okay, so let's finish off the rest of the integral, and what we have to do here is the 1/4 just carries along for the ride, and u to the minus 5, we got to do a plus 1 on that, so that ends up being u to the minus 4. Of course, whatever we put it to, we should divide off by, and then we have a plus c. So all in all, we have u to the minus 4 divided by negative 16 plus c. Almost there, but we should not give our answer in terms of u because we were asked the question in terms of x. And so what we're going to do is replace the u with the function of x that we defined it as, which is x to the 4 minus 8x3 plus 3. That's going to be 2 to the minus 4 divided by minus 16 plus c. Did I do it right? Well, I don't know. You tell me. We can all check the answer right here. Let's take the derivative and make sure that once we take the derivative, exactly the derivative appears inside this integrand right here. Okay, so don't forget about checking your work each and every time. It's really handy. The minus 4 cancels with the minus 16 to become a positive 1/4 right there. Then we get the step that was inside the parentheses, and that's going to now be raised to the minus 5 because we have to bring it down when we're taking the derivative. The plus c, of course, goes away. And on this term, don't forget that you have to multiply by the derivative of the inside, just like that. And now we notice that when we divide 1/4, when we multiply 1/4 times this right here, what we get is this quantity to the minus 5, and this 4 cancels that 4, so we get x3, and that minus 8 divided by 4 becomes a minus 2. Alright, we got the integrand back again, and so we check, and so we can go home nice and happy. See? Now once you get the hang of that trick, that's just about as bad as it's going to get in this class, so don't get, hopefully, too upset. Let's try that a couple more times, at least one more time, to make sure that you've really got the U-substitution down. Okay, so once again, this is going to be a problem where you're not exactly going to get your du, but you're going to get something that's very close. It's just going to be off by a constant, so you're going to have to figure out what that constant is. Here we're going to have the integral of the square root of x cubed plus 2 times 5x squared dx. Now the 5x squared is outside the square root, the x cubed plus 2 is inside the square root. What do you think I'm trying to get you to use for u? Well, usually the thing I pick for u is always inside of parentheses, and I don't see any parentheses here, but what I do see is a square root, and usually the first step when you see a square root is going to be to rewrite that in terms of a fractional power. Remember how helpful that was when we were trying to integrate using the power rule? We must see all radicals, square roots, cube roots, etc., in terms of their corresponding fractional powers, because then we can enact the appropriate power rule. Okay, now I see parentheses, and now that gives me a very good hint about what to use for u. And sure enough, if I let u equal the thing that's in that parentheses right there, when I take the derivative, the du part, 3x squared, and I'll put the dx over here because I'm trying to match it up with that. Oh man, this one kind of looks messed up, huh? This says 3x squared dx is what I wish I saw, and this says 5x squared dx is what you have. Alright, so the lesson is not only might it be off by a constant, but it might be off by a tricky constant. But a constant nonetheless. What number should we multiply both sides of this equation by so that instead of it saying 3x squared dx, it'll say 5x squared dx? What number should we multiply this by so it turns into a 5x squared dx? Well, I just wish there was a 5 on top instead of a 3. So here's what I'm going to multiply it by. I'm going to put a 5 on top, and I'm going to get rid of the 3. You see that? You can do that. The answer is 5/3. If you multiply both sides of this equation by 5/3, what happens is the 3 cancels, and the 5 shows up, and so you get a 5x squared dx, and don't forget you did that to both sides of the equation. So over here, this isn't du anymore, this is 5/3 of du is equal to 5x squared dx. Okay, that's what I had to do because that is what I had attached to my differential in the original integral. And so, as long as it's off by some sort of constant, you can do it. Even if it's a nasty constant like a fraction, you can still do it. Just force it in there and force it to look exactly like the thing that you have inside the integrand. Okay, so I'm going to replace this underlined thing right here with 5/3 of du. That's what I just figured out. Now the other part right here is that I just had u to the 1/2. So the integral becomes the integral of u to the 1/2. And then the underlined portion right there becomes the quantity 5/3 of du. And as usual, I'm going to take advantage of the constant multiple rule and pull the constant multiple to the outside so I can just deal with integrating a power of u. Each and every time, it ends up coming down to integrating a power of u in all of these instances. Okay? Alright, so the 5/3 is just coming along for the ride right there. And what happens to the u to the 1/2? Well, it becomes u to the 1/2 plus 1. Okay, what's 1/2 plus 1? That's 1/2 plus 2/2. And so that makes it a 3/2, right? And then whatever you put up there, you got to divide by exactly that same thing. And then when you have a fraction on the bottom, you might as well just flip that fraction so it comes up to the top. So you're going to have 5/3 times 2/3. You see how the fraction flipped when it comes up to the top? And then you have u to the 3/2. And so all in all, you get 10/9 of u to the 3/2. And that's when I'm going to throw the plus c on the end. Keep in mind, you really don't need that plus c until you get all the way to the end. Really, you could reserve it until after you've plugged the x back in and then you really get all the way to the end. Just don't forget the plus c, but don't worry about it too early. Like for instance, you don't have to put the plus c right here and then think that the plus c also got divided by 3/2. It doesn't matter because I don't know what the c is. So you don't have to like multiply or keep track of how numbers would times by the plus c. Okay, you just throw it on there in the end. And don't forget that you got to give me the answer back in terms of a function of x. So what did I call u? I called it x cubed plus 2. So that's really 10/9 of x cubed plus 2 to the 3/2 plus c. And that's what I'm claiming is my answer. But of course, I would like to make sure that I totally have my answer. So over here, I'm just going to check it by taking the derivative of what I see in that box. Okay? So I'm going to check my work right here. I'm going to take a d dx, the 10/9, just coming along for the ride. The 3/2 is going to jump down from the exponent. Then I've got the x cubed plus 2, and it gets to be to the 1/2, because 3/2 minus 1 is 1/2. Plus c went away. Don't forget the chain rule, times the derivative of the inside. Alright, and now I have to figure out all my little constants here. I've got a 3 and another 3, and that cancels with a 9. And I've got a 2 and a 10, and that turns into a 5. So really I have 5x squared times x cubed plus 2 to the 1/2. And that's the same thing that I was asked to integrate. Success! Yay! So I hope that you feel comfortable with this technique and also comfortable, very comfortable with the chain rule, because you're going to need the chain rule to check and confirm your answer.